and we will start our session. So the purpose of the session today is we want to make people aware of these advanced robotics capabilities that are available today that are kind of above and beyond what we've seen in the past. And today's session is an hour long. It's a quick preview of these 5 advanced robotics capabilities. And the intention is we're going to have follow-up sessions, one for each of these capabilities coming up in the next several months. But today we're going to have an hour session, and we're going to go through these one at a time and kind of give you a sneak peek at what these things are. And you can kind of decide, do they apply to me and my business or not? You can pick the ones that maybe apply and then jump in on the deep dive for that particular capability. So the agenda today, we'll start out, I'll do a little introduction here. I'm Brian Shea, I'm with Siemens. I'm in the manufacturing engineering group, support our manufacturing engineering applications in the US. And then I'm going to turn it over to our robotics experts, Shai Shamroni and Alex Greenberg from our manufacturing simulation business unit. They're going to give us a little state of the robotics industry, and then give us a snapshot of each of these advanced capabilities, each of these 5. Then at the end, Tom Hoffman, my colleague, is going to do a wrap up and Q&A, and Tom's going to be monitoring the chat window as we move along here today, and we'll finish up with questions there. So that's the agenda. So kind of as an introduction, I think everybody would agree that manufacturers have adopted both fixed automation and robotics in some of their processes where they fit. But when it comes to the assembly of manufactured products, a lot of the operations are still performed manually. And there's a number of reasons for that. There's some things that just have not been a fit for robotics before. And another reason is that programming the robots can be time consuming. And both of these issues are addressed by some of the capabilities we're going to be talking about today. So the idea is that these technologies that we're going to be looking at today expand the types of manufacturing processes that can be automated. So some examples might be things that require manual dexterity during assembly, like plugging electronic modules together, where maybe it's done by hand today because it's too hard to do with a standard industrial robot. But we're going to show you some solutions for that. Another example would be maybe some assembly operations that require a force feedback, like if you're fitting together plastic parts, they have kind of like a snap fit assembly. Not a good fit for standard industrial robots in the past, but you're going to see some things today where that would fit. So this is the list of the upcoming sessions. Today's the first one. Quick tour, going to look at all 5 of these capabilities. And the next session is 2 weeks from today. That's going to be looking at a process for automating robotic programming, motion planning, which can cut your engineering time by up to 80%. That's the next one up. You can kind of look at the schedule here. Number 3 is the one that's lets you do things like snap fit of plastic parts, things that require manual dexterity. Session 4 on February 18th, virtual commissioning of robots, and also AGVs, which maybe that's something that people haven't done a lot in the past. Session 5 is simplifying the process of setting up robot safety zones, and then the one in April is advanced techniques for robotic additive coatings. So these are the sessions, and we're going to show this again at the end. So if you don't get these dates down, you can see them at the end. So you can pick which ones apply to you, and we'll also be sending out invitations for each of these as we go along. So with that, I'm going to turn it over to Shai and Alex, and this is kind of the meat of the session here, where we kind of review these capabilities.
Thank you very much. Yeah, thank you very much, Brian. Can you make me a presenter because I can't show it?
Do it right now.
Okay.
You should be the presenter.
Okay, great.
And I'm starting to see your screen here.
Okay, excellent, excellent.
Okay, yeah, so you're up now.
Okay, thank you very much, Brian. So, as Brian mentioned, we want to give you, Alex and I, a brief overview of the way that we look at advanced robotics at the manufacturing business unit in Siemens Industry Software. I want to start with a quick overview or historical view of automation in general in the last 100 years or so. So the first manufacturing lines were very fixed. Only one product, maybe two products could have been manufactured on the same line. And they were also very manual, so there was no automation whatsoever. During the century, the 20th century, IT systems and electronics have developed and manufacturing became much more flexible, however, still very manual. And on the other hand, when electric motors and control theory came, manufacturing became much more automated, but still very fixed. Only a few number of variants could have been manufactured on the same line, no more than just a few. The main challenge and the main promise of Industry 4.0 is to enable manufacturing which is both flexible and autonomous, striving to reach lot size 1 manufacturing that for very small batches you could change the part and the environment will be flexible enough and autonomous enough to be able to adapt to the changing conditions and to the changing parts. So when talking about advanced robotics, there are many definitions out there what advanced robotics is. For us, advanced robotics is the area of robots which are smarter. They have sensors. They can interact with the environment and with each other on one hand, and on the other, they can also take decision. They are autonomous or very much automated. There are many applications involving advanced robotics, such as loading and unloading machines, machine tending, autonomous kitting, autonomous mobile robots, which support flexible manufacturing and matrix production, robots that are being carried by AGVs, robots for quality inspection, and robots which have safety features and can work together with human workers. So it's not one thing, it's actually a collection of technologies out there that make manufacturing much more autonomous and kind of promote it towards the direction of complete lot size 1 automation. We as a software vendor, as a simulation software vendor, would like to support you, our customers, who are now coping with those challenges and implementing automation with the right software that could give you the flexibility that you need and the capabilities that you need to plan this sophisticated and advanced robotics. In the next video, this is an illustration of a futuristic factory. It's an electric vehicle battery assembly factory. And as you can already see, it's not a linear line. The line is actually kind of a matrix, and each station has capabilities. Some of them can do the same, while logistics is completely separated from manufacturing. Logistics is done by autonomous robots that bring the parts on demand and just in time. In this case, these two batteries are being picked from the logistics center by the autonomous vehicle and being shipped to the manufacturing station where they are going to be assembled to the compartment, to the part of to the car. Another AGV brings the base, and now this robot that you see here, the KUKA industrial robot, will mount or assemble the batteries using vision system and force sensor, making sure that the batteries are exactly in the right place and nothing is broken during manufacturing, during production. Another evolving technology that we see is that also joining technology is changing due to different materials and combination of materials at the shop floor. So we expect to see also laser welding and gluing, adhesive and drilling and riveting technologies that require vision system support and advanced robotics also in the body manufacturing. And last but not least is robots that are being kind of bringing parts, logistics, just in time, and that can collaborate with human workers without the risk of safety, as they have the right features and sorry, supported by vision system that can ensure safety. Excuse me. So when you look at the robotics market, it is growing rapidly in the last several years. The picture here is before the COVID-19 situation, so I'm not sure that the numbers are that accurate anymore, but the trend is there. The market is growing rapidly. And what is interesting to see that both in manufacturing and logistics, the market share of advanced robotics is growing as well. So it is estimated that today about 20% of the robots in industry are advanced robots. And in logistics, AMRs, autonomous mobile robots in industry is about 30%. So there is a clear trend not only to implement more robots, but to replace the older robots with new ones and have kind of a mixed fleets of robots which are both traditional and advanced. Here you can see an interesting survey done by McKinsey. They asked almost 100 companies on their implementation and strategy of robotics implementation. And what we see that there is a clear majority of the responders said that they combine traditional industrial robots, AGVs, robotic cells of several robots working together, and collaborative robots. So the strategy today is to combine different robot technologies in manufacturing, and the need for offline programming software, virtual commissioning and simulation software is even higher than before, as the combination of robots requires a lot of interlocking and control and a lot of planning. To summarize the main challenges that the market that we hear from our customers today, it is still quite expensive to maintain a robot. According to research, about 75% of the cost in a lifetime of a robot, between 7 to 10 years, 75% goes to programming and setup. Only 25% goes for the actual hardware. So it means that the potential saving for robotics is in the area of programming, and the easier programming can be done, the better, and there is more potential for cost saving. And this is exactly where we are heading with, where we are looking with our software components to make it simpler for the users and to save time and money in that area. There is still a significant indirect cost of production downtime. Reprogramming requires in many times to stop production and to allocate engineering effort to reprogramming, which has an indirect cost. Still, robots are being used in an inflexible fashion. Although they can be extended to do more things, it is challenging to program the robot, and it takes time. So in many cases, robots are not fulfilling their full potential. We see that there is a lot of integration of sensors capabilities, which are much less expensive than before. So vision, force feedback, and specialized sensors are implemented in manufacturing and actually enable to do more complex automation in areas that used to be completely labor intensive before. And last but not least is the fact that in some areas, in some places, it is hard to find the right experts and the right talent to program the robot. Programming robots is an engineering work that requires knowledge in coding. And in some cases, there is kind of a shortage of expertise. So we are also thinking about how to make our products easier to use, so you can expand the population of users who can program the robots. What we want to do now is to walk you through 5 major capabilities and use cases that we believe have a lot of benefit. And I will ask my colleague Alex to take over now and walk you through some of the use cases. So Alex, go ahead.
Thanks, Shai. So to pick up where you finished just now, Shai, the first thing I would like to walk you through is the virtual commissioning technology. So before talking about virtual commissioning, let's talk about physical commissioning for a second. So usually if you would work without, simulation tools and the traditional way, when you commission a robotic line, you would usually see the different departments meet the first time when they come to the shop floor to set up the equipment and to start running and launching the line. So I'm talking about the mechanical departments, the robotics, and the PLC departments, the control departments. They would meet each other first time on the shop floor and start working out all the debugging and the, wiring, connecting everything together and making sure that the system runs. This is usually a very stressed and, so to speak, painful period in which there is a lot of problems to solve, a lot of issues to debug until you reach a good and robust running line. What we have here is a different approach, which says, okay, let's shift it to the left. And the idea behind it is to say, let's use the virtual environment in Process Simulate with all the robots, the robot programs, the virtualized equipment, fixtures, and so on, and connect it to the control equipment. It could be hardware in the loop or software in the loop, which has the PLC programs and the HMI. And by this, you shift left the entire work load that is associated with debugging everything, making sure that the robot code is robust, that the PLC code is robust, and that the HMI works correctly. You can validate mechanical sequences, you can validate manual modes, auto modes, safety scenarios, and all that helps you to achieve robust and mature programs on all sides, on all aspects. And this way, when you come to the shop floor, you basically are more dealing with the actual physical commissioning rather than debugging the software that you created for the robots and for the control equipment. So here you are a small example, a video. If you can activate it, Shai, please. So here you see a typical scenario where it's a software in the loop. So everything is running on one computer. You have Process Simulate on the right with everything virtualized, the robots, the fixtures, the grippers, and so on. Also, the signals are mapped to what you see on the left side, which is the TIA portal environment, our control authoring environment, software solution. And here during the runtime, you see how everything is playing together. You see the ladder diagrams on the left activated, and subsequently the virtual equipment is controlled and the entire process is orchestrated. So this way you can basically, as I mentioned, to validate all the different aspects of the system, starting from the simplest mechanical sequences and up to through the manual mode validation and up to the auto mode, continuous production, fooling the line, emptying the line, and so on, and safety scenarios. So this way you can even do it just on one laptop if everything is virtualized, and this is a very lean and efficient environment that allows you to do that. Shai, if you can switch to the next slide, please.
Okay, so Alex just presented how you can connect all the code together and make the virtual commissioning, make sure that you can debug everything. When it comes to path planning and to let several robots working together, the task of synchronization and interlocking is becoming even much more complicated. What we are offering here is a solution that we developed together with a partner from Boston, US, called Real-Time Robotics. Together we have a solution for multiple robot path planning and interlocking. All you need to do as an engineer is to focus on the engineering work, to define the final position of the robot, the waypoints in that case. So you don't need to worry at all about how the robot should get there and where the robot should wait for the other robot in order to avoid any collision, or how to make sure that there's no clash in the way between the robot and the environment. The algorithm that we implemented here and integrated into Process Simulate allows you to just define the final positions. All the rest is being done by the algorithm and being done in real time. Including the interlocks between the robots. Moreover, the algorithm would find the optimal way to do the job considering all robots working together. So in many cases, there will not be any interlocks at all because the algorithm will avoid them on the first place. In some other cases, there will be a wait, but the wait will be as minimal as possible. This yields tremendous saving in engineering. We did several pilots. We already implemented it with several customers in Europe, and we have now pilots running in the US and Asia Pacific as well. According to what we learned, you can save between 70% and 90% of the engineering time for the motion planning and interlocking. It's literally a matter of a button click to make everything work, and I'll show you a demo. It is also saving a lot of code. The robot code is actually much less. You have less lines of code because everything is done in real time. You don't need to program anything. And also the PLC code is reduced because you don't need to take care about any interlocks between the robots. The change management is also easy. We do the calculation prior to the simulation. So you run the calculation one time, and then during during simulation, the optimal path is being selected. So change is easy. You just need to move a waypoint from one point to the other, and run the simulation again without any need for reprogramming. Let me show you this example. Here you see 4 robots that weld this car bottom. Nothing was planned yet, only the final positions, only the weld points, and naturally they collide with each other and also with the environment. Now all you need to do is to connect each one of the robots to the service, to the real-time service that is integrated to Process Simulate, and do some configuration. You can set strategies of which robot should get priority over the other, or different types of strategies that you can set in the system. And you run the simulation again. Nothing was changed. You saw there was no path planning, no programming. You just run the simulation again. Now what happens, these 3 robots can work together. There's no risk for interlocking. And as you saw, one waits for the other, but for the minimal time. The 4th robot got into production only when it was safe for it to do the work, but no engineer or no human being had to set anything. Everything was kind of done in real time. So it's a sophisticated algorithm that is in many ways like a GPS. It calculates all optional roads, and during real time it will select the right road. And if there is a roadblock, in this case a robot interlock, it will find the best possible path during real time. So breaking through technology and a lot of potential there. There is dedicated hardware that is associated here, so it can run in real time. And if you want to learn more, you can join our second session. We'll give you much more details about exactly how it works and what is possible to do here. Okay, Alex, do you want to take this one?
Yeah. So regarding safety, the next topic. So that's another aspect, a very important aspect of robotic system. Recent years, most of the robot vendors introduced advanced safety features into their robots, And one of them is the ability to create safety volumes. So it's a widely used capability from the different robot vendors, which basically allows you to define virtual volumes around the different parts of the robot and the station. For example, around the end of arm tooling or certain parts or links of the robot, or around some important areas in the station, and kind of defined areas in which the robot is restricted to move into. And this, of course, allows a much more control over the safety of the station. Now, again, traditionally, you would do it like with the teach pendant on the shop floor, which is rather challenging for the shop floor operator, because you kind of need to imagine how this would look like and what to define, what sizes, and how it would, you would struggle to understand if what you defined is good enough and if it serves the purpose. So here, the 3D environment, the virtual environment, serves you very efficiently, because you can step into the virtual environment and design those safety volumes. You can create standard documentation for safety. You use the same environment and Process Simulate for all the robot vendors, and basically the fact that you can use also complementary other features in Process Simulate, like collision detection and other features, allows you to validate really well the definitions of the safety volumes and the overall safety structure of the station. Shai, if you can skip into the next station slide. So here you can see a demo. Again, so the standard Process Simulate work, you have the 3D environment of the station, and here you have a tool, the Safety Robot Manager, which basically allows you to create the different volumes, the different primitives, or combine them together. Here, for example, you do it around the gripper, and you have the various tools to shift it around, to control the placements, the placement, the size, and all the aspects. And eventually, when you finish, this is attached to the right part of the robot. And as you see here also, you can combine several primitives together into one block of volumes that would surround the gripper in an efficient way. So obviously, if you, as you can imagine, to doing that without visualization would be quite challenging. And here you see another volume which is defined in some part of the station, okay, which is limits, kind of creates a bounding box around the robot. And once you finish creating that according to your requirement, you basically can use those volumes with the standard features of Process Simulate, like I mentioned, with collision detection and other measurement and so on. So here in a second you will see some additional creation of volumes, like around the other link of the robot, additional links, as you can see here. So basically, this way you can alter the entire safety structure of the station, as I mentioned. And now you activate the collision with the right collision sets defined. You can include these volumes in collision sets. And basically, once you run the simulation, those volumes will be considered. And you can really validate that your safety setup is correct and works properly before you go to the shop floor. And this, of course, speeds the whole process up, and also reduces the risk of wrong definitions and running into issues on the shop floor. And as I mentioned, by the way, it's not shown here in the demo. You also can generate the right documentation out of this environment, so it also creates the right documents required for safety clearance. Okay, next topic. We're stepping into another area, and here we are addressing the challenge of the programming of robot. As Shai mentioned, usually you need quite high expertise in order to write robotic code. And here we introduce another solution, which is based on programming robots without writing any code. So you use templates instead of writing code lines for the robot. You can use templates, for example, from the most simple, like robot motions, move to state, or you can also program quite complex tasks which involve force torque sensing and vision. If you recall, Brian mentioned in the beginning the dexterity of humans. And as we see in latest trends, robots are acquiring this dexterity quite rapidly because you have quite affordable force torque sensors now. You have quite affordable vision cameras, and if you connect it all to the robot, it basically enables the robot to become much more dexterous and smart. But the thing is that you need to program it. You still need to program, and here this solution comes into place and allows you to program even most complex force control or vision control tasks just by using some predefined templates, and all you need to do is just parameterize them, and by that achieve very quickly a full program in a matter of hours instead of weeks or even months it would take to write this code for an expert. So Shai, if you can skip to the next slide. Here you see an example. Again, Brian mentioned in the opening, snap fitting, connecting plastic parts together, connecting PCB parts, inserting PCB components onto the PCB board, which is called through-hole technology. All this can be done with this tool without writing even one single line of code, just by dragging templates into the programming area from a library of predefined templates and parameterizing them very quickly. All this can be achieved offline in the Process Simulate environment. And in addition to that, which is new in Process Simulate, this allows you to connect to the actual robot with a LAN connection and basically program all the robot also interactively. So you have two options, both offline and online. You can immediately validate what you are programming with the actual robot and basically achieve a very robust and efficient programming process. Now, one note of how we implemented it. So we partnered with a company called Artimind from Germany, which developed this technology, and we partnered with this company and released a solution to the market, which allows you basically to enjoy the combination of Process Simulate advantages together with Artimind's technology plugged in, which allows you to use those templates to program the tasks that you see here now in the demo.
Tom, so can you take over? And... All right, so I think...
Yeah, Shai, do you pass the turn?
Make me a presenter.
okay. Okay, let me try to do that.
Or Brian can, right?
All right. Tom Hoffman. So stop sharing, right? This one. Okay. You should be able to share now, Tom.
Not yet.
Shai, I think you need to drag the small ball to Tom, you know, the small, yeah.
Yeah, there we go.
Thank you.
Okay, you see my screen, eh?
Yeah.
Okay, good. So good afternoon, good morning, I guess, good day, depending on where you're at. Basically, this presentation is the last in the series that we're talking about doing. It will be focused on code spreading methodology. It's not necessarily a new function that's being released in the application. Basically, it is a look at the power of the digital twin, the utilization of the tools in a managed way, combination of tools like NX and Process Simulate to develop methods to support the cold spray technology. You know, cold spray is similar to the additive process, just slightly different, right? Cold spray is a coating deposition technology that builds up material not by melting it in a typical additive method, but by using the impact of the materials on the surface to do the binding to that surface. So there's some masking and stuff that takes place. That picture on the right doesn't represent what we're trying to do. We have until, say, April. We're looking to get some formal release of the solution that was developed by our engineering team. And like I said, it's more about a process-based look at using robotics to replace what has typically been done as a manual method of spray guns pointed at a surface. The idea is that the robot is going to be much more consistent. It's going to be able to deliver higher quality. So higher quality yields a lot of different things, right? I'm going to waste less material. I'll be able to have a better focus. I won't have to rework anything, because the idea behind this cold spray technology is that you are providing a coating on top of worn parts for that refabrication process. So the less waste there is, the more succinct you are in control over your process. You're going to be able to do this much cheaper, much more consistent. Therefore, when they get it out there and they start to do the refurbished work, there'll be a lot less waste. So that is the last in the series. There will be, and like I said, it's not something that's a new technology necessarily, but it is going to show you how you can really use a digital thread to support these activities. The combination of things that we know, right? The robotics application, the NX application, developing paths and putting them on various types of surfaces. So it'll be an interesting piece of work when we get done with it, and something that you should be able to apply to a lot of different things that you're doing in the future. So with that, I will want to stop sharing, and I need to send this back over to Brian. Do I just take that ball and put it on you, Brian, or do you have to? Yeah, I guess I do. And Brian's going to bring up the slides so that we can close out the session for you folks here. So go to the slide just before that. There you go. So the next session is, you've seen some of the precursor to that, right? This the automated robotic motion plane, the RTR, real-time robotics type application. This idea that and those of you that program robots for a living know, especially in the simulation, that there are tools in simulation to get you from point A to point B and try to develop collision-free paths. But these tools are more advanced. They are can get you there very quickly, collision-free, and then working together. So this is 2 weeks from today. It'd be nice to see you all back here when we get in. It's only a half-hour session, so we're not going to use up all your lunch. You'll be able to finish your lunch. And have some more detailed discussion in there about everything in that session is for that. And then, of course, there'll be subsequent sessions, as Brian had said. From the 14th in January, we kind of give you a break over the holidays. And then we start back up in January. And like I said, the last session will be finishing up with that advanced robotics for additive coating, or basically cold spray technology. So next, Brian. Did you go to the next slide?
Hang on a minute.
Yeah. So from a Q&A perspective, there was I think there was a couple in the chat we've already kind of gotten to. Yeah, a lot of these things are modules in the price book, RTR and safety. They're additional line items. I think that unless there was any question, one of the questions was, what is the primary domain of advanced robotics? I think actually Shai did a whole slide on that. And, you know, in my opinion, some of this is based on, you know, in the old days, we used to do a lot of, even though we were taking everything and bringing it into the virtual world, there was still a lot of manual things we did relative to these robots by using tools and simulation to do it. So now we're actually providing tools. Brian, you want to go on mute? Brian, go on mute.
I thought I was unmuted.
No, mute yourself, please.
Oh, I'm sorry. Okay.
So I think that the advanced technologies from that aspect means that we're trying to provide tools to help simplify the process of doing simulation. One of the other questions on here, we look at, I think Shai's answered that question. Is safety robotics integrated into the C# API? Shai or Alex, you want to answer that one? Yeah, are they there? Yeah, they're there.
Tom, can you repeat, please, the question? There was some noise on the line.
Yeah, sorry. So the question is Safety Robots Manager integrated into the C# API?
So it is written on the API. As for is it exposed to for developers? I guess that this was the question. We need to ask the experts. I believe that we have a session for safety, and we will make sure to answer that question in that session in December 18th, I believe.
Okay. So that, Brian, I'll pass it back to you. That's basically the end of the session, but you want to bring up the agenda to make sure people's there for them to see.
Yes. And I think there was one more question there was a couple questions we didn't answer. One is on the virtual commissioning section. So you go through the virtual commissioning process, but then the question is, do you have to rewrite the robot programs to be able to dump them to, say, a Kuga, ABB, FANUC robot? I guess I'll take a shot at answering that. Is no, part of that process is you're using that software. The same software you're using to do the virtual commissioning is also creates the robot program, and you can download that robot program in the native language of a FANUC, an ABB, or any standards in 6-axis industrial robot. So I think that's it. That's all the questions I'm filled with.
Yeah. Maybe, Brian, to complete what your answer to, that's the whole idea of virtual commissioning. The idea is to test the actual robot code. So in this sense, you basically run the code as it would run on the robot. And as Brian mentioned, then, of course, it goes as it is to the robot controller, so you can be sure that what you simulated is what would run on the shop floor.
Yes. And there was another question about stack-up analysis, like can you deal with issues related to stack-up analysis? And I answered that on the chat window that yes, we can simulate quality issues like variation in the final assembly based on the stack up of the individual parts and the tolerances on the parts. But I'm not exactly sure if that was really the question that was being asked here in regard to robot programming. I don't know if anybody wants to comment on that.
I think I see that this is in the chat, right, Brian? Something
Yes.
like we can simulate validation in the final assembly that is caused by stack up of the individual parts.
Yes.
Well, honestly, I'm not really sure about exactly the question, what the question is exactly, but I assume it relates to the the simplified programming part with the templates. So again, we kind of simulate the nominal process of assembly. It is worth to mention that we are now in the process of introducing a physics engine into Process Simulate. So then this would also allow you to virtualize, for example, a force torque sensor on the robot. And this would allow you also to virtualize tasks that get feedback from this force torque sensor. And by that also to address variances in the product and simulate them. But this is something that we are still working on. It's not yet available, but should be available quite soon. I hope this answers the question and the intention.
Okay. All right. So I think we've addressed all the questions. Anybody else see any questions there that we didn't address?
I saw a question about CAD design and the CAD formats. So
Yes.
so the question was, what kind of CAD design is required, and can CAD be converted in between different types for simulation tool? So we support a format called JT. It's an open format from Siemens software, but we provide with Process Simulate converters from almost any CAD format, either standard interfaces, but also direct conversion from the major CAD systems. So it's quite standard and obvious to bring the geometry into Process Simulate, translate it to JT format. I hope I answered the question.
Yeah, I think that answers the question. So I think that's it. I think we're ready to wrap up for the day.
One last question. There was one question that says, is there any performance tuning to a VC to the PLC or troubleshooting to make the virtual time and the physical times line up better? I'll leave that to either Alex or Shai. I have my own opinion on that. So.
Right. So for our solution, the software in the loop solution, we have a virtual PLC called PLC Sim Advanced. We actually synchronize time. We have kind of virtual time that is identical for the simulation and the PLC. So if you use our software solution, there's no issue of time because they are completely synchronized. I believe that's the right solution for simulation in case that you found out that there are some issues of synchronization between hardware and software with the PLC.
Thanks, Shai. Brian, I'll leave it to you to close.
Okay. All right. So I think we're done for the day. I want to thank everybody for joining us. I hope that information was useful for you. And I think, just kind of looking at the attendee list, I see that, there's people from a lot of different industries here. I see, there's people that probably very familiar with robotics, and maybe some of these techniques we're talking about are, provide new opportunities. And I see some companies I think maybe haven't used robotics in the past, and maybe some of these techniques would make it applicable that you could use a robotics type of application for some of the things that are done manually now. So that was kind of our intention. I'd like to wrap it up now. Hope to see you on our upcoming series of seminars. We will make the recording available to everybody that joined today, and we'll be sending out invitations to these next 5 events as we move through the next several months. So thanks for joining. I'm going to quit recording, and that's the session for today.